Hello and welcome to Mr. Alvarez's virtual chemistry classroom. Today we'll be learning about the factors that affect the rate of a chemical reaction. Our aim for today is how can we qualitatively describe the four factors that affect reaction rate. There are four factors that affect the rate of a reaction: temperature, concentration, particle size, which is also surface area, and the usage of a catalyst. The first factor is temperature. Generally, temperature and reaction rate are directly related. That means when you increase the temperature, you are going to speed up the rate of the reaction. Whereas when you decrease the temperature, you are going to slow down the rate of the reaction. The reason for that is when you increase temperature, the particles move faster. And the faster the particles move, the more likely they are going to collide. Remember, for a chemical reaction to take place, you need an effective collision. An effective collision occurs when particles collide with proper speed and orientation. By increasing the temperature, you're speeding up the particles, and with that greater speed, they are more likely to collide, resulting in an effective collision. What we have here are two flasks. The one on the left is the cold temperature, measuring about 6 degrees Celsius, and the one on the right is the hot temperature, measuring about 88 degrees Celsius. We also have two balloons, one blue for cold, one red for hot, and two Alka-Seltzer tablets. I am going to take the Alka-Seltzer tablets, break them into pieces, and put them in each of the balloons. Then I'll put the balloons over the mouth of the flask. Let's see what happens when I lift up the balloon, pouring the Alka-Seltzer into the water. As you can see, the red balloon, the hot temperature, is blowing up, is inflating much more rapidly than the cold temperature. Remember, increasing the temperature will also speed up the rate of reaction. The second factor is concentration. Concentration and reaction rate are also directly related. As you can see, we have two containers of equal volume. The container on the left has more particles, which means it's a higher concentration, than the container on the right, which has less particles, which means it has a lower concentration. The container on the left will have a greater rate of reaction because there are more particles crammed in the same space, which means when they're moving around, there will be more collisions. The more effective collisions we have, that means we have more chemical reactions. So the container on the left will have an increased rate of reaction. For the next demonstration, what we have here are two plastic water bottles and two concentrations of hydrogen peroxide, H2O2. The one on the left is 3% hydrogen peroxide, and the one on the right is 30% hydrogen peroxide. So for this next demonstration, we will test how concentration affects the rate of reaction. I will pour equal amounts of hydrogen peroxide into each of the water bottles. Remember, the left one is 3% hydrogen peroxide. On the right, we have 30% hydrogen peroxide. Next, we are going to add manganese dioxide. We'll add just the tip of the scoopula and see what happens. A little fizzing, not much. Now let's test the 30% hydrogen peroxide. not only was there fizzing, but there was vapor that left the top of the plastic water bottle, and the water bottle actually shrunk. To the touch, the water bottle is hot. As you can see, the water bottle on the left, which contains the 3% hydrogen peroxide, looks normal, whereas the water bottle on the right, which contains the 30% hydrogen peroxide, has shrunk. The third factor is particle size, or surface area. How do they relate? Well, if we had two containers with equal masses of reactants, but the container on the left has fewer, bigger particles than the container on the right, which has more, smaller particles, the container on the left has a smaller surface area, whereas the container on the right has a greater surface area. The container on the left will have a lesser rate of reaction because there are fewer particles to collide. The container on the right will have a greater rate of reaction because there are more particles to collide. Remember, in order for a chemical reaction to take place, you need an effective collision with proper speed and orientation. So, an increase in surface area increases the amount of reactant exposed for the reaction. This increases the collision frequency and the reaction rate. How can you increase surface area? Well, you can dissolve the solid reactant in a solution, or you can grind the solid into a fine powder. The smaller the particles are, the greater the surface area it has. For this last demonstration, we will test to see how surface area affects the rate of reaction. For this demo, I will need a Bunsen burner, a metal scoopula, a watch glass, and some lycopodium powder. I will take the scoopula and scoop some lycopodium powder onto the center of the watch glass. I will then light the Bunsen burner. When you light a Bunsen burner flame, you always strike the match away from your body first before you turn the valve on, and then light from the side. As you can see in the flame, there are two cones, the hotter inner cone and the cooler outer cone. What I'm going to do next is I'm going to take the Bunsen burner, turn it upside down, and place the flame into the lycopodium powder. Lycopodium powder caught fire, but didn't really react too much. However, if I take the lycopodium powder and I throw it into the flame, you see there is a greater rate of reaction. Why? Because when I throw the lycopodium powder into the Bunsen burner flame, the lycopodium powder spreads out, more surface area. That way, more of the flame can interact, can react with the lycopodium powder, causing a greater, a faster, and increased rate of reaction. And the fourth factor is the use of a catalyst. A catalyst is a substance that increases the rate of reaction without being used up during the reaction. This is important. While a catalyst can be added to a chemical reaction, it's neither a reactant nor a product. Actually, when you would write a chemical reaction, a chemical equation, you would put the catalyst on top of the arrow. Since a catalyst is not used up during a chemical reaction, it can be used over and over and over again in subsequent chemical reactions. A catalyst, how does it work? It allows reactions to proceed along a lower energy path. On the Regents, you might see a multiple choice question stating that a catalyst provides an alternative energy pathway. What does that mean? Well, if we had just a regular potential energy diagram, a catalyst is not going to affect the reactants or the products. Just this hump in the middle So a catalyst is only going to affect the activation energy. Before, without a catalyst, if it required this much energy to initiate reaction, to activate the reaction, now the catalyzed reaction only requires this much energy to activate, to initiate the reaction. So the activation energy barrier is lower for a catalyzed reaction, which means with a lower activation energy barrier, more reactants have the energy to form products. More reactants can become products at a given time frame. So, as we said before, since catalysts are not consumed during a chemical reaction, it does not appear as a reactant or a product. Instead, a catalyst is often written above the yield arrow. So this is a common equation I'm sure you've seen before. 6 carbon dioxides plus 6 waters goes to yields 1 glucose and 6 oxygen molecules. This is the equation for photosynthesis. Photosynthesis, photo meaning light, synthesis to make, using light to make food. However, the light is not a reactant or a product. It's a catalyst, so we write it on top of the arrow. Finally, if we're talking about a biological catalyst, that is known as an enzyme. An enzyme is a specific type of catalyst. It has to be a biological catalyst. Like in your mouth, when you digest starches into sugars, in your saliva, you have an enzyme called salivary amylase. It speeds up the reaction in the breakdown, the decomposition of starches into sugars for digestion. Thank you for joining Mr. Alvarez's virtual chemistry classroom. Today we talked about the 4 factors that affect the rate of reaction. They are temperature, concentration, particle size or surface area, and usage of a catalyst. We also saw a couple cool demonstrations. Thank you again. I hope you learned something today. Have a good day.